example, we have a rod where the mass distribution is uniform. It has a mass m and length is L. It is fulcrumed at point O, so that this distance from this end is L by 4. Obviously from here it is 3L by 4, and right now this is horizontal, and these springs, they have spring constant K1 and K2 and they are vertical. If displaced by a small angle theta, we have to find the time period of the small oscillations. So if you remember, earlier we had done a question where we had found the time period of this mass which is hanging by a vertical spring, and over there first we found that is at this equilibrium position what are the forces acting on it, and then we displaced it by distance y. We found the time period, and the time period came out to be t is equal to 2 pi under root m by k. And from over there we deduce that is if we directly move this body from its mean position without bothering about that is how the forces they are acting at this equilibrium position, then we would have got the same answer. Similarly here also we are not bothered what is extensions or compressions in this spring. We are not bothered. As soon as we displace it by some angle theta, we will go for the extra restoring torques, that is a fresh restoring torques which come into play and which try to rotate the body towards its mean position. So as a result, what we do is, I remove this so that we have more space to write. This is, we have moved this body by a small angle theta, right? So over here we see that is mg, this theta is very small, almost small, so this almost still is like a horizontal rod only. So here when this is theta, so this will get compressed. If this will get compressed, this will apply a force like this, right? And this is going to be, let's say compression is going to be x1, and over there there is going to be elongation. This will get stretched, and this is, let's say, x2, right? So this is still almost equal to horizontal. So over here the force is going to be k1 x1. As now this has been compressed and this has been stretched, so this will apply a force almost perpendicular to this, that is k2 into x2. These are two forces which are acting. So once again if you see over here, that is this is almost, this rod is, which is at angle theta, is almost horizontal, and over here this has got compressed and this force is k1 into x1. This is fulcrum over here, this is a distance L by 4, and this distance is 3L by 4 from here to here, and over here this has got stretched. So as a result, this will apply a force k2 x2 over here perpendicular to this length, right? We will not be considering the torque of mg, because torque of mg initially also, when it was like this in its initial position, still that was also working, and right now it will also be working. So this is not a fresh torque. We are bothered about what are fresh torques which come into play and which try to put the body once again back into its original position, that is towards its mean position. So we find the torques about O. So it is torque about O is k1 x1 force into perpendicular distance of line of force and acceleration, that is k1 x1 plus L by 4. This is trying to rotate it this way. In which direction? In the clockwise direction. The torque of this force is also trying to rotate it in the clockwise direction. So both the torques, they are trying to rotate it in the clockwise direction. So they will get added up, that is clockwise movements, plus k2 x2, this is force into perpendicular distance between line of force and acceleration, that is 3L by 4. This is torque. So this torque is equal to I alpha, I about O. We know if we have a uniform mass thin rod, I about Cm, that is passing through its center of mass and perpendicular to its length, is ml square by 12. We have done it in finding the moment of inertia of this thin rod about an axis passing through its center of mass and perpendicular to its length. If we have to find at a distance L by 4, if this is L by 4, from here to here is L by 4, so obviously from center also, this L by 4 only. L by 4 plus L by 4, that makes L by 2. So this L by 4. So we have to find about O, this is about O. So I about O is ml square by 12 plus m into this is L by 4 square. We are using parallax theorem, m into x square. That is IO is ICM plus m into x square. So we have used this. From here we can find IO. So this is torque is equal to IO, we have over here IO into alpha, right? Over here we see that is x1. So over here in this equation we see we have alpha also, we have x1 also, we have x2. Also, whereas we have to now, our intention is to prove that is alpha is proportional to minus theta. We have to prove that. Where is theta? There is nowhere theta. So let's see where we can put theta. Over here we see that is this point is moving in a circle of radius L by 4. So this x1, length of the arc, is going to be L by 4 into theta. L by S is equal to r theta. This is L. So this is S, that is x1. What is r? R is L by 4. So S is equal to r into theta. So x1 comes out to be L by 4 theta. Similarly, this point, this end is moving in a circle of radius 3L by 4. So length of the arc, that is x2, comes out to be r. R is what? 3L by 4 into theta. Theta will obviously remain same. We know very well that is theta, omega, alpha, they are characteristic of the whole body which is rotating about some axis. So theta is obviously going to be same for all the particles. So theta is same. So from here x2 comes out to 3L by 4 theta and x1 comes out to be L by 4 theta. We can put it over here. So I0 into alpha is equal to K1. X1 is what? L by 4 theta into L by 4 plus K2 into x2 is what? 3L by 4 theta into 3L by 4. So from here I0 we have found out, alpha will come out to be, so alpha will come out to be something into theta can be taken out. So alpha is proportional to theta. Also, when we have moved it like this, restoring torque is in this direction, theta is in this direction, so they are opposite directed. So it is alpha is proportional to minus theta. So if alpha is proportional to minus theta, so we can very well say that this is SHM. If this is SHM, so we can use the time period t is equal to 2 pi under root theta by alpha. We can rearrange from here what is the value of theta by alpha. We can put it in this and we can get the time period for the small oscillations in this case.